Casting. This is the oldest known manufacturing process in which superheated molten material is poured inside a preformed cavity, and after solidification the casting is taken out. The casting process is broadly classified into two categories: sand casting, special casting. Molding, sprue design, gating design, core making, mold making, pattern making. Sand, mold, solidification, casting, heat treatment, inspection. This is feedback loop. Then machining, casted product. Pouring, superheated. It was poured into mold, which is solidified. Casting, then heat treatment, then inspection. Okay. To know the nomenclature, the upper portion is cave copper. This is drag. Lower portion is drag. This is pouring basin. This is dead weight. Strainer, sprue. This whole length is sprue. This is splash core. Vena contract. Here it is Vena contractor. There will be smaller one. Here it is skim bob. Uh, riser. This is riser. Cavity. Chaplet core. Core print. Core print. Cavity. Where cavity is required. A molding flask is the one which keeps the sand mold intact. For casting very simple shapes with small depth, a molding flask is one piece. In one piece is sufficient. But for casting complex shapes like dumbbell, the mold have to be in two pieces. In such case, the molding flask will also be in two pieces. The top part is called cope and bottom part is called drag. In the casting shape is further more intricate. Then flask is split into three pieces and the intermediate one is called as cheek. The vertical channel, which is mainly cut into cope part of mold, is called as sprue, which feeds the molten metal from pouring basin to horizontal channel along the parting line is called runner. The funnel shaped cavity is placed at top of sprue, and instead of pouring the melt directly into sprue, it is first poured in the pouring basin so that the molten metal enters the sprue with almost laminar behavior, so that the sand erosion can be avoided from the sprue wall. A ceramic filter called strainer is placed into vertical channel so as to filter the large size part impurities present into the molten metal. Sprue design. Let us consider a down sprue of height h2 whose cross-sectional area remains constant throughout its height. H1, H2, HT. H1 pouring basin, HT head of molten metal in pouring basin, HT is equal to H1 plus H2. Since 1 and 3 points are open to atmosphere, therefore gauge pressure P1 is equal to P3 is equal to 0. Applying Bernoulli equation between 2 and 3, P2 by rho g plus V2 square by rho g plus H2 is equal to P3 by rho g plus V3 square by 2g plus 0. Since A2 is equal to A3, V2 is equal to V3. P2 is equal to minus rho g H2. It can be observed that if cross-sectional area of sprue is kept constant, then negative pressure is created at point 2, due to which air will also be inhaled by the sprue along with molten metal, which will dissolve into the molten channel and will reach a mold cavity. After solidification, it may result in gaseous defects into the casting. This phenomena of air aspiration is called aspiration effect or breathing effect. To avoid the aspiration effect, there must not be any pressure difference between point 2 and 3, that is P2 is equal to P3, for which cross-sectional view of sprue must be varied throughout its height so that pressure throughout sprue will remain constant. P2 is equal to P3, A2 not equal to A3. A2 V2 is equal to A3 V3, V2 is equal to A3 by A2 into V3, V2 is equal to R V3, where R is equal to A3 by A2 is to avoid air aspiration. P2 by rho g plus V2 square by 2g plus H2 is equal to rho 3 by rho g plus V3 square by 2g plus 0. V2 square by 2g plus H2 is equal to V3 square by 2g. V2 square plus 2g H2 is equal to V3 square. R square V3 square plus 2g H2 is equal to V3 square. R square into 2g HT. V3 square is 2g HT plus 2g H2 is equal to 2g HT. R square minus 1 is equal to minus H2 by HT. R square is equal to 1 minus H2 by HT is equal to HT minus H2 by HT. R square is equal to H1 by HT. R square is equal to H1 by HT. Area ratio to avoid aspiration is R is equal to A3 by A2 is equal to root of H1 by H2. Root of H1 by HT. A2 A3 A3 by A2 is equal to root of H1 by HT. From top inversely proportional to root H. As per above expression, the cross-sectional area of sprue should be decreased linearly to avoid aspiration, but in above expression we have not taken care of frictional losses, boundary layer phenomena. Hence, during practical design, the sprue design cross-sectional area is decreased parabolically. At bottom of sprue, velocity will be very high. Hence, to avoid any sand erosion, a ceramic splash core is provided at bottom of sprue. As molten metal enters horizontal channel from sprue, its direction changes and hence there will be some contraction associated with molten channel at beginning of runner, due to which atmosphere may dissolve in molten metal as runner channel at its start will not run full. Hence a compensation for vena contracta is provided in beginning of horizontal channel. To filter the remaining impurities, a skim bob is provided in horizontal channel. Out of remaining impurities, the heavier ones settle down in lower half of skim bob, while the lighter ones float up and are entrapped into upper half of skim bob. Now almost pure molten metal enters mold cavity through the gate. If hollow sections are required, then core is placed in the cavity with the help of core print at appropriate position and further supported by chaplets to avoid any displacement in its position due to net force acting on it due to buoyancy of molten metal. F net is equal to rho 1 minus rho 2 into Vg. Rho 1 density of molten metal, rho 2 density of core, V volume of core, G is equal to 9.8 meter per second square is equal to 32 feet per second square. Chaplets must be made up of same material being casted, and their design and placement must be in such a way that during the liquid state of metal it supports the core, but before phase change they melt and fuse uniformly along with the metal getting solidified. Otherwise the unfused chaplets will be severe defect in casting. Due to this reason the use of chaplet is minimized. After filling the mold cavity, the rest of molten metal rises into riser cavity. The riser has following two functions. It shows that whether the casting is full or not. It compensates for first two stages of shrinkage. If it is open riser, then it fulfills both functions, but if it is blind riser, then it fulfills the second function only. Shrinkages during casting. Temperature time, this is TP, then latent heat fusion, local solidification time. This is total solidification time, and TF it keeps on decreasing till room temperature. Cooling curve for pure metals. Cooling curve for alloys except eutectic, it will be a range from Tm to Tf, latent heat of fusion, Tm greater than Tf, Tp, To. During casting, the superheated molten metal undergoes the following three different stages of shrinkage. Liquid shrinkage, it is associated with decrease in volume of superheated molten metal when its temperature decreases from pouring temperature to melting temperature. Phase change shrinkage, the shrinkage is associated with reduction in volume of the molten metal when it changes its phase. In case of pure metals or alloys with eutectic composition, this phase change phenomena occurs at constant temperature, but in case of alloys except eutectic, the phase change phenomena occurs in a range of temperature. The first two stages of shrinkage altogether is termed as solidification shrinkage, and the first two stages of shrinkage are compensated by risers. Solid shrinkage, this is the shrinkage associated with change in volume of solidified casting when its temperature reduces from freezing temperature to room temperature, and it is compensated by shrinkage allowance on the pattern. First stage liquid shrinkage, second stage TM solidification shrinkage, TF third stage solid shrinkage. These two are mostly compensated by risers. Solid shrinkage is compensated if a contraction compensated by positive shrinkage on positive shrinkage allowance on pattern. That means if it is going to contract, then what will happen, like we have to provide extra positive allowance, extra dimension, then even if it contracts, then it will come to correct dimension. Expansion, there are very few examples which will expand: antimony, bismuth, silicon, germanium, compensated by negative shrinkage allowance on pattern. During first two stages of shrinkage, as the metal shrinks, the molten metal flows back from riser to the mold cavity and hence compensates for shrinkage. Since the purpose of riser is to compensate for the first two stages of shrinkage, therefore liquid metal in riser cavity must not solidify. Until molten metal in mold cavity is solidified, in riser cavity must not solidify until molten metal in mold cavity is fully solidified. In other words, solidification time of riser must be more than solidification time of casting. The solidification time of molten metal in any cavity depends on following two factors: total heat content of the melt in cavity, rate of heat transfer from surface of cavity. Therefore, it can be easily observed that solidification time in any cavity must be directly proportional to some function of volume and inversely proportional to some function of area. If area is more, then heat loss will be more, so time for solidification will be less. Similar. So, based on observation, Chauvelin now suggested the following expression for solidification time. Solidification time T is equal to K into V by a whole square, where V is volume of respective cavity, A is surface area through which heat transfer takes place, K is solidification constant, second per meter square unit. Solidification constant K depends on following factors: type of material being casted, type of sand mold, mold material reaction. Risers are mostly designed for their minimum surface area for any given volume. So spherical riser will have minimum surface area, but even though they are not preferred because theoretically it will have you a point contact, hence no metal transfer. Moreover, spherical risers will be weak and break during hand lining. Side riser, top riser. Side riser means it will be like this, top riser means it will be like this. In case of side riser placement, the heat transfer takes place from all the surface area of riser as well as mold cavity, and these all surface areas are accounted during calculation of solidification time. But in case of top riser placement, there will be no heat transfer from bottom of riser and top of casting and top of casting. Therefore, these surface areas will not be accounted during calculation of solidification time of riser and casting riser and casting respectively, because top of casting is not considered. Design and compare two risers of same volume of which one is cylindrical and another is square parallelopoid. Uh, in case of both the side riser and top riser, V is equal to pi r square L cylindrical. V is square parallelopoid A square B. Vc is equal to pi r square h is equal to Vc by pi r square. AC is equal to 2 pi r square plus 2 pi r h. AC is equal to 2 pi r square plus Vc by r. For surface area to be minimum, dSc by dr is equal to 0. So h is equal to 2r is equal to d for side riser. Tc is equal to k into v by a whole square. Finally, Tc is equal to k into d by 6 whole square. Square parallelopoid side riser, Vs is equal to a square h is equal to Vs by a square. As is equal to 2a square plus 4ah. ds by dA is equal to 0. Then h we will get h is equal to a. Ts is equal to ka by 6 whole square. Given that volume is equal, A cube is equal to 2 pi R cube, compare TC and TS, we will get TC is equal to 1.17 TS, TC greater than TS. Cylindrical side riser will be preferred because the riser should have more solidification time. For top riser, the bottom one will not be considered. Bottom area will not. VC is equal to pi r square h remains same. AC is equal to 2 pi r h plus pi r square. Only pi r square. And remaining same. Then we will get optimum h is equal to r is equal to d by 2. The above h is equal to d. Ts is equal to k into vs by s whole square. Uh, whole square. K into d by 6 whole square. A parallelopoid a square h VC is equal to a square h DAC, here only one a square DAC h is equal to a by 2, TS is equal to k into a by 6 whole square. TC is equal to 1.17 TS, so cylindrical riser is preferred. Method of riser design. Shrinkage consideration method. As per this method, riser volume is taken as 3 times of the solidification shrinkage volume, and this design is checked for satisfying the following condition: Tr greater than Tc, K into Vr by Ar whole square is equal to K into Vc by Ac, Vr by Ar greater than Vc by Ac, Mr by greater than Mc, where M is equal to V by A is modulus A by V ratio cooling characteristic. If design satisfies above condition, then riser dimension is used. But if riser dimension does not satisfy above condition, then new riser size is calculated for limiting condition Mr is equal to Mc. Modulus method. As per this method, while designing the riser's modulus is taken 20% more than casting modulus. That is, MR is equal to 1.2 MC. Keynes method. As per this method, at first we find freezing ratio x and volumetric ratio y. Then this xy point is plotted against the Keynes curve. If point lies above Keynes curve, then riser design is satisfactory and sound casting will be produced. Otherwise, casting will be defective. Freezing ratio x is equal to mr by mc is equal to v by a riser by v by a casting. Volumetric ratio y is equal to vr by vc. X is equal to a by y minus b plus c. A, b, c Keynes constant. X so y, it will be like this: freezing ratio, volumetric ratio. The curve will be like this. This side sound casting, this side defective casting. Everything given. X is equal to mr by mc, y is equal to vr by vc. If we substitute, Naval's research method. This method was developed in American Naval's laboratory to cast slabs. As per this method, at first we find shape factor x and volumetric ratio y. Now x comma y is plotted against Naval's curve. If the point lies above curve, the casting will be sound, otherwise defective. Shape factor is equal to L plus W by T. Length, width, this is thickness of casting. Volumetric ratio y is equal to VR by VC. Volumetric ratio, shape factor, this is sound casting, this is defective casting. Shape factor for hollow cylindrical casting of height h and diameter di and do. It has to be cut as a slab because this is designed for slab. L is equal to h, W is equal to pi into do plus di by 2. Pi into do plus di by 2. T is equal to do minus di by 2. Yes, shape factor is equal to h plus pi by 2 into do plus di by 2 by do minus di by 2. Shape modulus. Shallow cylinder T is equal to do minus di by 2 th by 2 into t plus h cube a by 6 cylinder a d by 6 sphere d by 6. Pattern is replica of part being casted with some modification in its shape as well as size. The size modification are due to fact that several types of pattern allowances are taken onto the pattern, while modification in shape is mainly due to the fact that patterns may contain projections core print known as core print. If casting requires a core and need to be made hollow, properties properties of pattern material should easily be able to be shaped, joined, and worked upon. Should have low density and low melting point. Should be strong, hard, and durable. Should have very good resistance to wear and abrasion. Should have very good resistance to corrosion and chemical reaction. Should be dimensionally stable and unaffected by varying climatic conditions. Low cost, readily and easily available. Pattern material would do less costly but dimensionally unstable. Can easily absorb moisture. Cracks, internal and external, may develop during summers. Much more easier to be shaped and joined. Most commonly, mahogany, pine, teak wood are used. Metal, more costly but highly durable, mostly unaffected by varying climatic conditions. Most commonly, aluminum alloys, cast iron, steel, brass are used as a pattern material. plastic. In case of phenolic resin bonded sand molds, the sand mold material will have a tendency to stick to wooden and metallic pattern, and hence in this case very hard plastic polyurethane is used as pattern. Wax used in investment casting material mostly, since it is very soft, therefore it can be shaped very easily. Highly complex and intricate shapes can be made from wax, since it is very smooth, therefore mold walls are also very smooth, resulting in casting with very good surface finish. Limiting of wax in limiting of wax is that it is very soft, hence it can deform under force of ramming or can bend under its own weight. Mercury used in mercast process below room temperature. Used in mercast process below room temperature. Note, in case of wax and mercury, the pattern need not be removed. Instead, the pattern along the sand mold is brought to room temperature in case of mercury, while in case of wax, the pattern along with sand mold is brought to 100 degrees so that the wax melts and poured out. Polystyrene, it is used in full molding. Following are different type of patterns: single piece pattern or a simple pattern. These are simplest form of pattern and used when a shape of a casting is very simple as well as depth is small. Split piece pattern, it will be like this. If the shape of casting is such that the pattern cannot be taken out from sand mold without disturbing the sand mold, and depth of casting is too high, then the pattern is split into two pieces so that one goes into cope and another goes into drag. Gating pattern: if gating system is also integrated with split piece pattern, then it eliminates the hand cutting of gating system and improves production rate. Match plate pattern DT. This is like match plate. If you we can put this type of pattern is used in machine modeling. In this type of pattern, the cope half and drag half are mounted on two sides of a match plate. The match plate thickness should be such that it matches the contour of casting. Loose piece pattern, in case of casting where the projected sections in a direction perpendicular to vertical surface, we use loose piece pattern. In this pattern, the projected section is made as loose piece and is temporarily fastened to main piece. After ramming the sand, the main piece is withdrawn, followed by the loose piece. During ramming, there will always be a chance of displacement of loose piece, and therefore highly skilled workers are required. Skeletal pattern: in this pattern, at first a skeletal is prepared with the help of wooden strips which resembles the casting, and at time of molding, the skeleton is tightly filled with sand mold which act as a solid pattern. Sweep pattern. Sweep pattern. This is sweep pattern. If rotated, in this case, a plate type of sweep pattern rotates within the sand mold, producing large size cavities having rotational symmetry. The following different types of allowances are provided on pattern. Shrinkage allowance: this allowance is provided on pattern to compensate for third stage of shrinkage. If tendency of solidified material is in third stage is to expand, then negative shrinkage allowance is provided, that is pattern is made smaller in size, while if the tendency of casting is to contract, then a positive Shrinkage allowance is provided on is provided, that is pattern is provided in larger in size. Shrinkage allowance directly proportional to quotient of thermal expansion and is always taken linearly, that is independently on each dimension. The rate of contraction of various materials during solid shrinkage is as follows. Solid shrinkage material gray cast iron dimension shrinkage allowance. These are just no need to remember these values. These are just values given so that we can compare, like cast iron 0.125, aluminum 0.155, magnesium 0.173, cast steel 0.251. And as size is increasing, shrinkage allowance is decreasing. Solid shrinkage varies in the following order: gray cast iron less than aluminum less than magnesium less than cast steel. Gray cast iron has least solid shrinkage. Cast steel has highest solid shrinkage. It can be easily observed that as the size of casting increases, solid shrinkage decreases. Percentage volume shrinkage of important cast metals as follows: metal or alloy percentage volume shrinkage. These are values also no need to remember: pure aluminum, zinc, Al, copper alloy, gold and tin, bronze 5.5%, white iron 4%, copper 4.5%, plain carbon steel, lead, grey cast iron 0 to 1.8%. Grey cast iron, one very important thing to be remembered: only in second stage there will be expansion. This is the only exception. Gray cast iron, only in second stage there will be expansion. First and third stage there will be compression. So positive shrinkage allowance is only provided as third stage is compression. Draft allowance for easy with, if it is straight line like this, then there is some draft is provided. For easy withdrawal of pattern from sand mold, the vertical surfaces of pattern are tapered out a little, half to 2 degrees, which is called a draft allowance. Draft allowance is always provided at as extra material, that is it is positive shrinkage allowance. Then internal sections require larger draft allowance compared to external sections, because the strength of sand mold near the inner section is relatively less. Shake allowance during the withdrawal of pattern. Some shake will be required to withdraw the pattern easily, due to which sand mold, which is wrapped all around the pattern, will move back, leading to enlarged cavity. Therefore, a shake allowance, which is a negative allowance, is native allowance can be provided on pattern, but its magnitude will totally depend upon skill and emotion of worker. Therefore, instead of providing shake allowance, it is taken care by providing some extra draft allowance. Machining allowance during sand casting, it is very difficult to avoid mold metal reaction. Therefore, surface property of casted product is always poor. Hence, it needs to be machined, which requires extra material, otherwise the casting may become dimensionally inaccurate. Hence, machining allowance, which is a positive allowance, is provided onto the pattern, that is pattern is made larger in size. The wooden pattern which will be used to produce metallic pattern will always require a machining allowance twice than that of machining allowance provided to metallic pattern. The wooden pattern which will be used to produce metallic pattern will always require a machining allowance twice that of machining allowance provided on metallic pattern. Distortion allowance. Casting which has just solidified in is very weak and hence distortion prone. Especially when shape of casting is U shape, V shape, which are thin and long, or when there are long and thin projected sections from vertical surfaces of large size casting. Hence, distortion allowance is provided onto pattern in opposite direction with the opposite direction of distortion with the same magnitude with which the section distorts. Like for example, if it is going to distort like this afterwards, then minus the pattern is made inside like theta, then at last it will come like this length L. Distortion allowance theta directly proportional to L by T. Note: in case of wax pattern, mercury pattern, polystyrene pattern, the draft allowance and shake allowance are not provided because in case of wax patterns, the mold along with pattern is heated to temperature above 100 degrees centigrade so that wax melts out, while in case of mercury pattern, the mold along with pattern is brought to room temperature and hence mercury pattern melts out, while in case of polystyrene pattern, the molten metal is poured without withdrawing the polystyrene pattern. As superheated molten metal comes in contact with polystyrene pattern, it evaporates out. Properties of sand mold: strength: given the mold is freshly prepared, it contains moisture and hence it is called as green sand mold. This green sand mold must have enough strength for handling purpose, which is called green strength. As soon as molten metal is poured, the moisture evaporates out from sand mold surrounding the different channels and the mold cavity. That this dry sand mold must have enough strength to avoid any crack or deformation. This strength is called as dry strength. To check green strength and dry strength, a universal sand strength testing method is used through which loads can be applied in all three modes, that is tension, compression and shear. For testing, we use a specimen made up of same sand mold composition, and it is cylindrical with h is equal to d is equal to 5.08 centimeters. Loads are applied onto specimen and the load onto which fracture appears in specimen in the respective mode gives respective strength. For dry strength testing, similar specimens are baked for enough time so that the moisture evaporates out, and then loads are applied by mounting specimen on USSTM in all three modes, and loads at which fracture appear gives us respective strength. It is found that dry strength in all three modes is approximately 10 times more than green strength. Collapsibility core DO decreases during casting. The metal undergoes different stages of shrinkage and hence it undergoes either through some stages of expansion or contraction. If this shrinkage is resisted by sand mold or core, then cracks may form into red hot solidified cast leading to cracks called as hot tear, and hence to avoid this sand mold material adjacent to solidified casting surface must have moved back to allow shrinkage during cooling. This property of sand mold is called as collapsibility. Refractoriness: it is a property of sand material to withstand very high temperature of molten metal without showing any signs of burning or fusion. Adhesiveness, this is the property of sand mold material to stick to any other material. In this case, the molding flask, the adhesiveness totally depends on quality and quantity of clay into the sand mold. Adhesiveness depends on clay permeability or color or porosity. This is the ability of sand mold mixture to pass out burnt gases, air, and moisture through it. This depends upon size of pores, and size of pores further depends on size of grains in sand mold. Hence, longer is the size of grains, larger will be the pores, and hence larger will be the porosity. That is, permeability directly proportional to grain size. With varying water content into the sand mold, permeability also varies. P water content 8% maximum variability then decreases. When water content is very less, then there will be many loose sand particles which will fall inside the pores and hence will resist the burnt gases, air, and water vapor trying to pass through the pores, and hence permeability will be less. As the water content increases, various loose sand particles will be bound together, forming larger grains, and hence size of pores will increase, while amount of loose sand particles will decrease, increasing the permeability. At 8% water content, permeability will be maximum, but beyond 8% permeability will decrease, because when water content goes beyond 8%, then sand mold material will not be able to absorb any more moisture, and hence moisture itself start accumulating into pores, and hence permeability decreases. Permeability is quantified by a permeability number, which is found by permeability test as follows: air 5.08 centimeters, 5.08 centimeters. Pn is equal to Vh by Pat. This is permeability number is equal to Vh by Pat. V is equal to volume of air is equal to 2000 centimeter cube. H is equal to height of specimen is equal to 5.08. P is equal to pressure in gram per centimeter square. A is equal to cross sectional area of specimen is equal to pi by 4 into 5.08 whole square. T is equal to time to pass of the air in minutes. Permeability number is equal to 501.28 by pt. Permeability number is directly proportional to porosity of sand mold. Flowability, it is property of sand mold to flow over the pattern and fill each and every corner around the pattern within the whole flask properly. Friability, this is the property of sand mold to crumble down during the removal of solidified casting. Composition of sand mold mixture: sand up to 70 to 80%, either ordinary silica sand or zirconia sand ZrO2. Zirconia sand is chemically more inert than silica sand. Clay 20 to 30% if acts as binder when activated by water. The most popular clay used in casting are kaolinite or fire clay Al2O3 2SiO2 2H2O, and bentonite Al2O3 4SiO2 NH2O. Water up to 8%, it activates the clay. Other additives up to 2%. Cereal binders such as corn flour, dextrin, etc. improve both green strength and dry strength. Sawdust improves collapsibility by burning slowly as well as increases permeability. Pitch, it is a byproduct of petroleum industry and improves dry strength and refractoriness. Coal dust, thick carbonaceous layer is deposited at the inner surface of cavity, and once the molten metal is poured, The metal comes in contact with the carbonous layer, which burns and creates a very thick layer of dense and carbonous gases. Hence, this layer restricts the mold metal reaction, resulting into better surface finish of casting. This is called a facing sand. This is called as facing sand. Baking sand, this is small amount of used and burnt sand added to sand mold to improve refractoriness of sand mold. Grain size number, the American Society of Testing and Materials suggests that grain size number n and average number of grains kaplan per square inch as follows: n is equal to 2 power n minus 1. Grain size number, n is grain size number, the kaplan is average number of grains per square inch. Calculation of mold filling time. Top gate, in case of top gate, the in gate will be situated exactly at top of casting. Discharge into filling time is equal to volume of casting. Filling time is equal to volume of casting by discharge. TF is equal to capital A into capital H by AG root 2G HT. AG root 2G HT. If AS is equal to AR is equal to AG. TG is equal to AH by ASVS is equal to AH by ARVR is equal to AH by AGVG if AS not equal to AR not equal to AG. Bottom gating system, capital H DH P1 is equal to P3 is equal to 0 open to atmosphere, P2 is equal to P2 prime is equal to P2 double prime at the same datum line. Let us assume that height DH is filled in cavity in time dt, and head of melt is in basin remains constant. Bernoulli equation between 1 and 2, P1 by rho g plus V1 square by 2g plus HT is equal to P2 by rho g plus V2 square by 2g plus 0. This is 0. P2 plus V2 square by 2g is equal to HT. Applying Bernoulli equation between 2 double prime, P2 double prime by rho j plus V2 double prime square by 2g plus 0 is equal to P3 plus V3 square by 2g plus H. This is at H it is considered. P2 double prime is by rho g is equal to P2 by rho g is equal to H. V2 double prime V3. From 2 and 1, V2 square by 2g is equal to HT minus H. V2 is equal to root of 2g. HT minus H is equal to Vg, velocity at ingate. Assumption, cross section area of ingate of gating system is uniform. Assumption, Ag Vg dt is equal to A into dH. dt is equal to A into dH by Ag root 2g into root of Ht minus H. Integral 0 to T of dt is equal to A by Ag root 2g into integral 0 to capital H dH by root of Ht minus H. TF is equal to 2a by Ag root 2g into root Ht minus root of Ht minus capital H. If a head of molten metal in pouring basin is equal to height of casting, then time taken to fill cavity through bottom gate will be exactly double that of through top gate. If Ht is equal to capital H, then T bottom is equal to 2 T top gate. Through the top gate, time taken to fill cavity will be less and flow will be highly turbulent, and then therefore top gate is only suitable for large size casting. Through bottom gating, time taken is more, but sand erosion is less, and hence it is suitable for small size casting. Parting gate, if the gate is situated exactly at parting line, then it is called as parting gate. The drag half of molding will fill like top gate, while cope half of the flask will fill like bottom gate. Step gate, it is used for filling very small sized cavities. The size and number of ingots are normally increased from top to bottom. Design of gating system. The goals of designing gating system are as follows: to minimize turbulence, avoid entrapment of gases into mold, to get enough melt into mold cavity before metal starts to solidify, to avoid shrinkage, to establish best possible temperature gradient so that there is no dimensional changes and variations from exact size due to shrinkage. Incorporating filtering systems for trapping the non-metallic inclusions present in mold cavity. Types of gating system: pressurized gating system, non-pressurized gating system. A decreases, P decreases, V increase. Pressurized gating system: A decreases, P decreases, V increases. The total cross-sectional area decreases towards cavity. Back pressure is maintained by restrictions in metal flow, which reduces aspiration as the sprue always runs full. But because of restrictions, the metal flows at high velocity, leading to more turbulence and chances of erosion. Non-pressurized gating system: A increases, P increases, V decreases. Total cross-sectional area increases towards cavity, and restriction is only at bottom of sprue. The channel will never run full, hence chances of aspiration will be high, but sand erosion will be less. Gating ratio: it is ratio between cross-sectional areas of sprue runner and gate. Gating ratio 1:2:1.5 produces a very good steel casting which is nearly free from erosion and minimized oxidation, but larger gating ratios such as 1:4:4 will might favor the formation of oxidation defects. Sprue runner gate. Defects in sand casting: mold material defects, cuts and wears, cuts and washes appear as area of excess metal. The molten metal entering mold cavity erode the molding sand from near the gate. This is caused if the mold not having enough strength, or if velocity of molten metal entering mold is very high. The former can be taken care by proper choice of molding sand or proper ramming, while the latter can be taken care by proper design of gating system. This cutter wash will be there. Drop and scab. Drop or scab appear when a portion of face mold lifts or breaks down, and the recess thus made is filled by metal. When metal is poured into cavity, gases may be disengaged with such violence as to break the sand, which is then washed away, and the resultant cavity will be filled with metal. The reasons can be uneven ramming, low permeability of sand mold, or a high moisture content. Metal penetration appears when molten metal enters into gaps between sand grains, resulting into rough casting surface. This occurs because sand is coarse, or no mold wash applied onto the surface of the mold. The coarser is the sand grain, the more will be metal penetration. Fusion occurs when the sand mold material adjacent to molten metal fuses with the molten metal, giving it a brittle and glassy appearance. The main reason is that the sand mold has low refractoriness or pouring temperature is too high. Swell under influence of heavy metallostatic forces, the mold wall may move back, causing a swell in dimension of casting. A proper ramming will take care of this defect. This is swell. Gaseous defect, large size, elongated or spherical cavities present in casting is called blowholes. These are blowholes. Very small size pores created inside casting due to dissolution of hydrogen gas is called as pinhole porosity. These are pinhole porosity. Uh, b- these are gaseous defect. Uh, blowholes present near casting surface is called blister. These are blowholes present near casting surface are called blister. Small size crater type cavities present at surface due to blasting of burnt gas is called scar. Pouring metal defects misrun. It is caused when metal is unable to fill mold cavity completely and therefore leaves behind unfilled cavities. Cold shut. It is uh, it is caused when two different streams of molten metal in mold cavity do not fuse together properly and therefore forming a discontinuity in casting. Misrun. It will go till here, then stop unfilled cavity. Cold shut, there will be unfilled cavity here. Misran and cold shut. Misran and cold shut defects are caused either by lower fluidity of molten metal or when section thickness of casting is very small. Fluidity can be improved by changing the composition of the molten metal as well as the mold and by increasing pouring temperature. Fluidity, it is ability of molten metal to flow and fill the entire cavity properly. It depends upon several factors as follows: directly proportional to pouring temperature, directly proportional to degree of superheat, inversely proportional to viscosity of molten metal, composition of mold, metal mold reaction. Fluidity test, spiral test. In spiral test, the molten metal is poured in spiral mold and the distance that molten metal travels inside the mold gives us a measure of fluidity of molten metal. The cross-sectional area of a spiral mold remains constant throughout its length, then it is called as rod test, but if cross-sectional area varies throughout the length, then it is called as V test. Vacuum test, molten metal is sucked inside glass tube with help of vacuum, and the distance that molten metal travels inside the tube before getting solidified gives us a measure of fluidity. Solidification in casting. This is liquid, this is solid. The one that is shaded is solid. End effect. Uh, End effect. These are hot spots. Divergent heat flow, convergent heat flow. Divergent heat flow, convergent heat flow, solid to liquid. End effect. Primary dendrites unidirectional. Primary dendrites bidirectional. From here also secondary dendrite. This is bidirectional. Primary dendrite, secondary dendrite, porosity or shrinkage cavities. Unidirectional, bidirectional. Center line shrinkage, progressive. The geometric shape of mold cavity has direct effect on type of solidification. At the end of tunnel type geometry divergent heat flow occurs which causes the area of casting to cool faster to cool faster than the surrounding area. This is called as end effect. Large cavities do not cool as quickly as surrounding areas because there is less heat flow. This is called as rising effect. Rising effect. Large cavities corners can create divergent or convergent heat flow called hot spots. Directional solidification is solidification which occurs from farthest end of casting, then works its way towards the sprue. In directional solidification, primary dendrites form near surface of mold cavity, then they move towards sprue. In bidirectional solidification, at first primary dendrite forms near mold surface, which moves towards the riser, but after some time a secondary dendrite also appears somewhere within the liquid metal, and then works its way towards both riser and primary dendrite. Now the place where two dendrites meet, micropores are created which cannot be compensated by riser and hence leading to defects such as porosities and shrinkage cavities. In case of progressive solidification, also called as parallel solidification, the solidification starts at walls of casting and progresses perpendicularly from that surface. Most of the metals and alloys shrink as as the material changes from liquid state to solid state. Therefore, if liquid material is not available to compensate for this shrinkage defects are formed. In other words, if bidirectional and progressive solidification dominate unidirectional solidification, the shrinkage defects are formed. To avoid bidirectional and progressive solidification, and to promote unidirectional solidification, following measures can be taken. Chills external, internal, external, direct, indirect. Chills are used to promote unidirectional solidification. The chills can be placed either adjacent to the cavity, direct chill, or can be placed somewhere where within the mold, internal chill. The chill are made of material with having high melting point, high thermal capacity, and high thermal conductivity. Chill promote the unidirectional solidification as it increases rate of growth of primary dendrite, not giving any chance for formation of secondary dendrite. Internal chills are metal pieces which are placed in mold cavity to absorb heat and to promote more rapid solidification, since some of metal will melt during operation. In sin, it will absorb not only it will absorb not only the heat energy but also some heat of fusion, since internal chills ultimately become part of final casting. Therefore they must be made up of same material being casted and must melt and fuse properly with casting. They are made up of same material being casted, must melt and fuse properly with casting. Padding uh, thinner padding for production of sound casting. The temperature gradient should be such that no part of casting remains without metal during full solidification cycle, for which the thinner section should be tapered. The thinner section should be tapered towards heavier section to change progressive solidification to directional solidification. The tapering of thinner section towards the thicker section is called padding. However, this will require extra metal. If padding is not provided, then centerline shrinkage or porosity will appear into thinner section. The directional solidification can also be used as a purification process, since most of impurities will be more soluble in liquid state than into solid state. During solidification, impurities will be pushed away by solidification front, causing much of finish casting to have insignificant concentration of impurities while the last solidified metal will be enriched with impurity which can be scrapped off or recycled. Special casting process, shell molding, dump box, fines and phenolic resin, heated pattern. Now these heated pattern inversion, it is inverted, then it will be formed like this. Then this is separated, this is separated, there two types are joined like this. Then here pouring, the sand is mixed with a thermosetting resin and then allowed to come in contact with heated metallic pattern 200 to 300 degrees centigrade. A shell skin of about 3 mm to 4 mm thickness of sand and plastic based thermosetting resin phenol formaldehyde adhere to the pattern. Now shell is removed from pattern. The cope and drag shells are the two halves of shell are kept in flask with necessary backup material, and then the molten metal is poured. After solidification, the shell is broken and casting is taken out. Advantages: better dimensional accuracy, a smoother surface due to fine grain used, a very thin casting can be made that very small amount of sand is required. Limitations: expensive pattern, useful for small size casting only, highly intricate shapes cannot be obtained, sophisticated and complex equipment is required for handling shell mold. Application: cylinder heads, connecting rods, engine blocks, piston rings, etc. Slush casting: in slush casting process, a permanent die mold cavity in two halves is generally used. The molten metal is poured into permanent die cavity and is filled properly. In this filled properly, thereby solidification starts from the surface of permanent die. Once required thickness solidified, then die is inverted, rest of molten metal is poured out. The two die halves are separated and we obtain hollow castings with very fine surface detail but with varying thickness. The pattern is used mostly for making ornamental objects such as lamp bases, halo states, candlesticks, etc. from low melting point material. T is equal to C1 root tau plus C2. T thickness, T tau time. Investment casting, pattern making. Pattern is made like this. Pattern cluster. Pattern cluster is made like this. Then investment. Pattern making, several wax patterns are produced with the help of pressure die casting or centrifugal pattern assembly. Multiple wax patterns are attached to central wax sprue to create a pattern cluster or tree. To attach the pattern, a heating tool is used to slightly melt the designed wax surface, which are then pressed against each other and is left to cool and hardened. As many as several hundred patterns can be assembled into single tree. Applying investment material, the ceramic mold is known as investment, is produced by repeating a series of steps: cleaning, coating, stuccoing, and drying. To clean the wax pattern cluster, we apply alcohol coating. Involves dipping the pattern cluster into slurry of very fine refractory material and then drying to create a uniform surface coating. The fine material are used in first step, also called as prime coat, so as to preserve the fine detail from mold. Stuccoing applied relatively coarse ceramic particles by dipping the cluster into fluidized bed or by placing the cluster in a rainfall sander. Now these invested clusters are left to dry completely, which can take 2 to 3 days. The drying process can be accelerated by either applying vacuum or minimizing the humidity. The common refractory material used for investment can be silica, zircon, alumina, and various aluminum silicates. During prime coat, zircon-based refractories are commonly used because zirconia is less likely to react with molten metal. The binders used to hold refractory material in place mainly include silicate binders such as ethyl silicate, colloidal silica, sodium silicate. Dewaxing: once the ceramic mold has fully cured, then the clusters are placed in furnace so as to melt or evaporate the wax inside. Most of the shell failure occurs at this point because the wax used to have higher thermal expansion quotient than the investment material. So wax as the wax is heated, it expands and introduces stresses. To minimize this stress, the wax is heated as rapidly as possible so that outer wax material can melt and drain quickly, making space for rest of wax to expand. Preheating the mold is now subjected to burn out so as to remove any moisture and residual wax to sinter the mold. The preheating allows the metal to stay liquid longer so that it can better fill all mold material, all mold details, and can cool more uniformly. Pouring: the preheated mold is placed in open side up into a tub filled with sand. Now the molten metal may be forced or poured inside the cavity under gravity or centrifugal force. Divesting: the shell is now hammered, media blasted, or vibrated, water jetted, or chemically dissolved, such as in case of very precise casting. Advantages: excellent surface finish, very high dimensional accuracy, almost any material can be casted. Limitations: the overall cost is very high, especially for small production run. Very large size castings cannot be made. Labor cost is very high. Application: used in space industry and power generation, and to make single crystal directionally solidified jet engine blades and turbine blades. Used for fabricating firearmed hammers, firearmed triggers, pistol barrels, small satellites, and space buses. Centrifugal casting: in this process, a permanent die which can be either made up of graphite or grey cast iron is used, which is in two halves. The mold can be rotated vertically, horizontally, or at some inclination at very high speed. At first, the internal surface of rotating mold is coated with refractory material, and then the molten metal is introduced, which rises into mold due to whirlpool action and is held against mold wall by centrifugal force until it solidified. During cooling and solidification, the low density impurities will tend to move towards internal surface, which can easily be scraped off later on. No cores are required and halo sections are produced easily. Advantages: fine grain structures at outer surface, and the casting will be free from gaseous impurities, shrinkage cavities, and porosities. Very good dimensional accuracy at external surface, production of halo sections without core. There will be no need of gates and runners, therefore the casting yield is almost 100%. Casting yield is equal to volume of casting by volume of metal poured. Limitations: internal diameter will vary, shape is limited, that is only rotationally symmetric products due to fine grain machinability will be poor. Fine grain machinability will be poor. Spinning equipment can be expensive. Squeeze casting: molten metal is poured into open die. A punch is advanced into die to metal, which applies pressure less than forging while the part solidifies. Therefore, thereafter, the solidified casting is knocked out by using ejector pins. It overcomes problems with feeding the die. Hence, it produces near net and highly detailed parts. Plaster casting: a slurry of plaster, water, and various other additives is applied over pattern and is allowed to set. Thereafter, the pattern is removed and the pattern mold is baked to remove excess water, and then the mold halves are joined to create mold cavity after pouring and solidification. The plaster mold is broken and casting is taken out. It produces high dimensional accuracy and smooth surface finish. It is used for casting thin sections with intricate details, but can be used or only low temperature non-ferrous materials like aluminum and copper. Pit molding: a large size pit is created out of sand, concrete, cement, and then molten metal is poured into it. After solidification, the pit is broken out and the large sized solidified casting is called as an ingot, which can be further be broken down into billets, brooms, or slabs. Continuous casting: it is also called as strand casting, in which molten metal is solidified directly into semi-finished billets, blooms, or slabs. In this process, at first the molten metal is poured into very large size pouring basin called as tundish, from which it is allowed to flow into very long water-cooled mold where it solidifies into required dimension and hence eliminates the breakdown of ingots. Die casting: in die casting, the molten metal is introduced into permanent mold generally made up of grey cast iron. It is introduced under gravity, then it is called as gravity die casting. If it is injected under pressure, then it is called as pressure die casting. Pressure die casting is useful when the cavity is highly intricate and molten metal is unable to fill every detail under gravity. For example, casting aluminum alloy pistons are casted by gravity die casting, while carburetors are casted by pressure die casting. During casting, if the furnace is part of die casting machine, then it is called as hot chamber die casting, a machine in which metal starts in a heated cylinder and piston forces the metal into the die, but it is only suitable for casting metals having melting temperature less than 400 degrees centigrade, such as lead, tin, zinc. In furnace, if furnace is not the part of die casting machine, then it is called as a cold chamber die casting machine, which is suitable for relatively high melting point temperature materials such as copper, brass, aluminum greater than 600 degrees centigrade. Advantages: good surface finish and dimensional accuracy, molten metal mold, hence rapid cooling and fine grained structure. The mold can be used multiple times, minimum finishing operations, thin sections can be casted. Limitations: mold life is limited, especially with casting of high melting point materials, high initial mold cost, part size is limited, porosity may be problem. Applications: pistons, cylinder rods, kitchenwares, gravity die casting, carburetors, automotive parts, bathroom fixtures, toys, etc. Pressure die casting.
Full mold casting, it is an evaporative casting pattern process which uses a polystyrene pattern surrounded by sand. Much like sand casting, the metal is then directly poured into mold which vaporizes the pattern, allowing pattern to fill the mold, and then vapor is simultaneously extracted through the sand. The polystyrene pattern is cheaper than wax, and since the metal vaporizes the polystyrene pattern, therefore the first metal into mold cools more quickly than the rest, which results in natural directional solidification. CO2 molding. In CO2 molding, at first the mold is prepared by reaction between sodium carbonate and water. Sodium silicate and sand is first blended together, then treated with the CO2 so that it hardens the silicate binded sand mold, and hence strength of mold increases. The strength depends upon treatment time with CO2. This process is very fast and can produce molds in very less time as compared to other process. If core is required, then it is also treated along with mold, and due to high strength of mold, core does not require any other reinforcement. Buckle effect due to buckle effect due to poor expansion of sand, high pouring temperature. Rattle effect due to poor expansion.